Welcome to the SciMax channel. I'm going to follow up on the self-driving lab light demo that we talked about in the last video. And today I want to look at some topics in reproducibility, what differences can we be sure about, and whether there are interactions between the channels to help understand some things that I saw yesterday. So the setup here, again, I use very minimal little bit of Python code here to define a function measure, and measures using a cached get results function that returns all the data. We're only going to focus on the 620, 510, and 470 results. And just to remind you, what happens is we put in some integers from 0 to 255 for R, G, and B. That turns on an RGB LED at those levels. And then there are three channels that we're measuring at 620 nanometers, 510 nanometers, and 470 nanometers. And it's worth noting that these are not equidistant apart in nanometer space. So there's over 100 nanometer wavelength difference between 620 and 510, but only about 40 nanometer difference between G and B. And so if we don't have very sharp wavelengths coming out of the RGB, then there can be overlap on these, and we're actually going to see that that happens. Okay, so we're going to run a lot of experiments today. So I have previously run these and cached them. So everything you see in here will be reusing the cache, and you'll see kind of why. It takes about 7 to 10 seconds per run from the time it leaves my house here in Pittsburgh, goes out to Salt Lake City, runs the experiment, captures the data, and comes back. That is typically a 7 to 10 second experiment. Okay, so one of the things I wanted to get a handle on is reproducibility, or what is the variation in the measurements that one might expect. And this is important because we're fitting models, and that means that there's noise in the data, and we need to have an idea of how big that's going to be. And so I started this by just asking how reproducible is this? Can I make the same measurement at 50, 50, 50, 50 different times? So this is about 5 minutes worth of experiment time, and thankfully these experiments are free, because if I had to pay even $1 an experiment, this would be a $50 experiment. So here I use a unique label for each one, and I just make a July 4th, that's today, and this is a base, and then I put this counter in here, and this is going to now accumulate those measurements, and this is going to load the cached results, so it's super fast. Then I can look at the average, so we get averages. This is close to what we saw before. About 12,000, about 8,300, about 12,000 over those 50 measurements, and you can see the standard deviations are pretty small on this scale, only about between 7 to 10. And if we look at how these change, so we should look at how they change over time. So when I made these, I just made them sequentially, and you might wonder, are they truly independent? There should, we don't want to see any trend in time. So what I do is just subtract the mean from each one, and then we can plot this and see it as a function of time. So this is what it looks like. You can see for the first 30 measurements, it seems to just fluctuate around, and then the last 20 measurements, it appears like there's a trend. And that's not great, but the scale of this is still on the order of 1 to 2 of those standard deviations, and that's still small compared to 12,000. So this is something you ought to keep in mind. There does appear to be a trend here, and that could mean a whole bunch of things. It could mean something is heating up and a resistance is changing, so a voltage shifts. It could mean something is degrading. It could mean all kinds of things. Maybe the temperature is changing over in Salt Lake City, and that's affecting something. You really don't know. And so this is a potential nuisance variable that has to be considered in all measurements going forward. And if you don't figure out that it's not an issue, then you don't know if it's not an issue. Okay, we can also look at the histograms because we might think that there ought to be a normal distribution. And when I look at these, I don't see something that is clearly a normal distribution. It is only 50 measurements, and it is like approximately bell-shaped. There is a maximum in the middle. There are some tails on the end. But 50 measurements does not appear to be enough to establish with certainty that these are normally distributed. And in fact, they are not continuous. We get integers back, and so we're getting a range of integer values, which may make it challenging to assume normality. But for the rest of this, I'm going to do it anyway, because I don't have a better assumption for this distribution. Okay, so that's what we get. You see this range of like plus or minus 20 on here gives you probably like a 95% confidence interval, and so there's no question that this is different from this and this is different from this. They're not even on the same in the same space. No overlap at all. Okay, how about if I change from 50 to 51 in some channel? What happens to our measurements? So that was the next thing I wanted to do. So I ran 3 sets of experiments where I just perturbed one of those channels by 1. So we have 51 in red, 51 in G, 51 in B, and then we want to see whether or not the differences are obvious and significant. All right, so I'll run this one. This also just loads from the cache, and here I'm going to look at whether there's any temporal shift, and it's not real obvious here. You see these are kind of scattered around 0. Maybe there's been something like red goes up and down and something like this. Not totally random, but also nothing to be super concerned about on the scale here. So that's good. Now let's look at the analysis. So what I want to do is compare the baseline red RGB values to the shifted RGB values. And so we'll do this for red first, and we'll look at each channel. And so here's what we see. The baseline is in black, and when I increase it by 1, you see a huge shift, very clear, no overlap, and so these two are unambiguously separate. And the red histogram is clearly larger than the black one. And in these two cases, it's not super obvious. The histograms overlap a lot. You would probably look at that and say, changing the red channel does not change green and blue. We can be a little more quantitative. If I calculate the mean change here, we get a mean difference of 300, and then practically 0 for the other ones. And if I normalize those by the standard deviation of that base measurement, this is called a z-score. And if z is bigger than about 2, it's significant, and if it's less than 2, it's not significant at the roughly 95% level. And so this difference here of almost 30 is highly significant, and these differences are not significant at a 95% level. All right, so the red channels, easy to see. You change red, it's 100 nanometers or more away from the other channels, and you don't see any influence. Let's look at the G channel. So here I've changed just the G setting, the green setting, and if I look at these, the story's not as clear, or it is clear, it's just not the same. So it looks like there's no change in red. Red and gray overlap substantially. The green is different by about 200, and the B is also quite different, right? And there's no overlap. When you see these distributions with no overlap, you can qualitatively say the difference is significant. It's only when they overlap that you have to worry about, is the average actually different, or could this be an artifact? So here again, we look at the two means, 198 and 81, and if we look at these z-scores, these two are greater than 2, and for this system that means that these are both significant differences. So apparently if I change the G setting, it changes the B setting, the B output and the G output. Okay, and then last, let's look at the B channel. So we do the same thing here. It looks like there's unambiguous change by 1 unit in the B. That's to be expected. Not a great deal of clarity here. These two overlap a lot, and these two overlap in the middle. So that means that these may be significant. The averages may be different. So let's have a look at something quantitative. We see 200 is the mean difference in the RGB channel, and 23 is kind of bigger than the standard deviations that we've seen before, and the z-score is just a little bit above 2, which means that the 95% confidence interval, this difference is actually significant, even though it's not very large. And you can tell it's not large because these overlap, right? So the mean is somewhere here and somewhere here, and that difference is about 24, but it's probably significant. Might not be an important difference, but it is a real one. Okay, so that kind of made me wonder then, how much do these channels interact with each other? And so I set up an experiment here where I made, looks like about 20 experiments to go from 0 to 100 at every 5 interval, and then we're just going to change the R, the G, and the B setting in each one. And then we're going to make a plot to show how the intensity in each channel changes with those settings. All right, so I'm going to skip the code. It's not super interesting, and just get to the main results. So what this shows here is as I vary the R channel, right, you see the red output go up, and it's pretty linear except at the lowest settings, and you see hardly any change in the blue and the green. A little tiny change, it's not totally flat, but it's very low. And then when I vary green, you see the green channel goes up quite a lot, and it's also roughly linear except at the lowest settings, but you also see the blue line, the blue channel is going up. So the green element in the RGB LED is obviously emitting some blue light that's getting picked up, and the red channel is hardly changing. And then as I vary the blue, of course the blue line goes up, again linear at high settings, a little non-linear at low settings, and the green goes up a little bit more than the red in this case. So it's interesting that we didn't see a real obvious correlation between blue and green above, but you can see that there is some crosstalk between these different channels. All right, that has an impact on what we're going to model because we will want to account for interactions that the G channel can influence what's being measured on the blue output. All right, the last thing I wanted to think about, you might remember that we did this optimization to try to find out what are the RGB settings to get 10,000, 10,000, 10,000. And it wasn't super clear to me before, although it should have been. When you look at the diagonal of the linear fit, they were order 200 to 300. That means if you change the RGB setting by 1, you expect the intensity to go up by 100 or 200 or 300. And so if we're at 9900, then changing one of those by 1 would make it go to like 10,200. And so we probably aren't actually able to get exactly 10,000 for any setting because of the integers and discretization. So I wanted to visualize that and see it. And so here I set up a loop. I set a random seed. This is actually important for the way I did this because I don't store the list of numbers that we're going to use. In the list, I'm just randomly choosing one of these 3 states for each RGB setting. And if I use this seed, then next time I run this, I'll get exactly the same numbers. So what I'm doing here is just picking, one of these states, one of these states, and one of these states. These are, the middle line here is the optimum solution we found before, and we're just going to run 150 of them and try to visualize what state space is actually visible. Now to do that, I use a scatter plot, and so I'm going to plot the R column on the x-axis, the G column on the y-axis, and I'm going to use the z-axis, the B column for the color, and that way I'm going to get a two-dimensional plot. And that's shown down here. And in fact, this shows quite nicely that you do not have continuous access to all the output space. So there are a 3x3 array for the most part that represent the 3 R values, the 3 G values, and then the color are the 3 B values. And you can see there are big white spots in here. So at 10,000, 10,000 right here, we're probably not able to access that with any setting because it is in between the discrete states that happen when you change, from 50 to 51 or 35 to 36 or 42 to 41 or something like that. There are some outliers out here. Those are kind of unusual. I assume they're real and don't know why they're there. But these are 1, 2, 3, 4, 5, 6 out of 150 have some kind of outlier. But all of these observations have some interesting implications on trying to do an optimization problem to find a solution, because it seems like if you want the 10,000, 10,000, then this cluster is the closest one, and all the other ones are further away. But it also means that it's not super obvious to me how one goes about building a surrogate model. Of course, we can fit this data to a surrogate model, but surrogate models are continuous, and then we have to ultimately solve like a mixed integer problem for any optimization here. So I think that's an interesting kind of problem, one that we'll probably come back to another day, because if you're going to do active learning on this system, then that means you're building a surrogate model and then using that to probe for the next kind of experiment. And so I wanted to get a more intuitive sense for what this instrument does and what kinds of things we have to be thinking about before I jumped into doing that. Okay, so that's mostly all for today. This was largely an exercise in using my ELN to kind of document these results and experiments and figure out what kinds of models would be useful and what the uncertainties are and what kinds of limitations we might face in building surrogate models. So I think that's probably what I'll try to do next is figure out a surrogate model active learning loop that we can use to find a set of conditions that will get us closest to, say, 10,000, 10,000, 10,000. All right, that's it for today. Thanks for listening, and we'll see you next time.